That's why women don't have it.
She realized that
Like how it's yeah. I was like, this is too low.
All right. Let's get started, folks. So I want to start by rewriting Green's theorem, because that's in a way kind of the foundation of all of this. So Green's theorem in the plane. So reminder, the Green's theorem only works in the plane. Green's theorem says that the line integral around a simple closed curve, f dot dr, is equal to the double integral over a simple connected region of dn dx minus dm dy dA, where f is m I hat plus n j hat. Now, we've mentioned it several times. I want to point out again that Green's theorem is a generalization of the fundamental theorem of calculus, where we have the integral of some quantity inside a region is equal to some other thing evaluated on the boundary of the region. So in Calc 1, we have the integral over between two real numbers is the antiderivative evaluated at the endpoints, at the ends of the interval. So this Green's theorem is really telling us the same thing. Some quantity integrated over an area is some related quantity evaluated on the boundary of that area. And we came up with a couple of other forms of Green's theorem. We talked about doing the line integral of the tangential component of f, and we talked about integrating the outward normal component of f around that simple closed curve. And we came up with a couple of forms. We said that the line integral over our curve of f dot n ds was equal to the double integral over our region of the divergence of f and here we were integrating the outward component of f around the boundary of the region, and we said that was equal to the divergence of the field integrated over the entire region. And we said that integral of f dot dr, the tangential component, was equal to, if we thought of f as a three-dimensional field with a 0 k hat component, that this line integral of the tangential component was equal to the curl of the field dotted with the k hat vector, so the upward component of the curl, the vertical component of the curl. So what we're going to do, what the divergence theorem and Stokes theorem does, is extends both of these ideas to three dimensions, and instead of talking about a line integral, we're going to talk about a surface integral. And here, instead of talking about a line integral and a double integral, we'll talk about a line integral and a surface integral. So the divergence theorem and Stokes theorem are extensions of these forms of Green's theorem. So in other words, the divergence theorem and Stokes theorem are a more general expression of Green's theorem. So as we go further, we're getting more and more general expression of this idea that something integrated on the interior of a region is some related quantity evaluated at the boundary of the region. All right, so let's talk about the divergence theorem first. Divergence theorem says that the surface integral of f dot n ds equals the triple integral of del dot f dv. And we need to make some specifications. D is a solid region that's why we have a triple integral bounded by the closed surface S. So here S is a closed surface. It's not, we're not talking about the integral up, the flux upward or the flux downward. We're talking about the total flux through this closed surface. So we could, to be more precise, we could do that. To say we're talking about a closed surface. And what this is telling us is that the integral of the normal component of f over the surface is equal to the divergence, integral of the divergence through the solid. You'll also hear this rarely. You'll hear this theorem called Ostagrodsky's theorem, because this Russian mathematician Ostagrodsky was the first to prove it, or the first to publish it, sorry. But we don't hear his name because in Russia at the time there were strange political things going on. And he was denied a degree because he was an atheist. So he published this theorem, but in Russia they didn't give him a degree, so he doesn't get much recognition. Also, more commonly, you'll hear it called Gauss's theorem, because Gauss proved it first, but he didn't publish it until later. What's that? He had it in his private papers.
Oh, okay.
And right, and so several years later he decided, oh, I'll submit it to publish it. The proof is not complicated, but it's kind of long and there are a lot of details. But and the book goes into the proof, so you can look in that section of the book. The idea, the basic idea, is that so this is a very, very general idea. Is that inside the solid, if we have a little small piece of volume, so a little cube whose volume is dV, so very, very tiny little chunk of volume in there. The idea is that the flux in because it's a small enough piece of that solid, that whatever flows in there is going to flow out. But at the surface, when the field, whatever it is, the material, whatever, flux in, here's our surface. Now it goes out. And it's outside, it flows out the surface of the solid. So we're saying the divergence in the solid is equal to the surface integral of the normal component of F over the surface, because when at the surface, whatever flows in ends up flowing out of the solid. So that's the very, very general idea of how we prove this. All right, how we use the divergence theorem. When is it useful? It is useful for finding the flux outward through a closed surface. And we would want to do that when the surface integral is difficult. Just like we use Green's theorem to simplify a line integral. A lot of times a double integral over our region is easier than the line integral around the boundary. So when the surface integral is complicated, and especially when the surface is made up of piecewise smooth surfaces. For example, a cube. So you had a cube as one of your flux calculations in your homework. You had to do you have 6 surfaces that you have to deal with. The other day we talked about a closed paraboloid. So we had to find the flux upward through the paraboloid portion of the surface, and we also had to find the flux outward through the bottom. If this, what was our surface in our integral of the day? X squared plus y squared equals 1. Cylinder. If that cylinder had a top and the bottom, without the divergence theorem, we'd have to find what we did for our integral of the day, the flux outward through the cylindrical, the round part, the curved part of the surface. Then we'd also have to find the flux upward through the top and outward through the bottom. So 3 different surface integrals. With the divergence theorem, you would apply the divergence theorem and do the integral over the volume inside that cylinder. And I want to show you. This just popped into my head. So I did my presentation for my comprehensive thing that I had to do for my degree. I talked about the heat equation in a sphere. But I want to show you a slide here. It's always nice when this happens. Okay. So I was doing the heat equation with insulated boundaries in a sphere. So 3-dimensional solution in spherical coordinates. Where we are. Second step. Apply the divergence theorem.
Boom.
So we were talking about the heat flowing out of this closed surface. So we're doing the triple integral of the rate of change of the temperature in the surface per unit volume equals the outward flow of the heat through the surface, and we apply the divergence theorem. And the del dot phi gives us our nice differential equation. Partial differential equation. Because it varies with respect to time, with respect to x, with respect to y, and with respect to z.
Right.
And then, no, this is This is that equation transformed into spherical coordinates.
Oh gosh.
Yeah, Ben?
Nice.
Yes.
Oh, you know, I just like it. You know.
It's like an angle in the middle of the day.
And
What
the
is setting angles?
what's that?
Follow mathematical.
Zenith from the angle from the positive z-axis. Positive z is the zenith.
Oh, okay.
It's like five.
Phi.
You definitely do that.
I did because I know what.
So in physics, sometimes they measure phi from the horizontal instead of from the z-axis. In mathematics, we usually measure it from the positive z-axis. In physics, sometimes you'll measure it from the positive x-axis or the positive y-axis, from the xy plane. So anyway, let me just for fun, let me show you some of the. There's a few slides later. Yeah.
So how long did it take to input all those equations?
A lot of time.
15 minutes.
Yeah, a lot of time. And I could because I needed to send a copy of the PowerPoint to the people who were sitting on the committee. I couldn't use my equation editor, so I had to use the Word equation editor, which I hate using. So yeah. And it turns out, did I tell you this?
Answer 0.
There's our solution to that differential equation.
Wow.
Interestingly, though, this is the first time. So I'm 52 years old. So you know, I don't know if I told you this. I was telling somebody. So in chemistry, you talk about all the different orbitals, S and the P, and you see drawings of the weird shapes of the orbitals. So it turns out that the solution to Schrodinger's equation, which is quantum mechanical equation that describes how the particles behave in spherical coordinates. So for an atom, the angular part of the solution is the same as the angular part of the solution to the heat equation. And those orbitals, the shapes of those orbitals, come out of this angular part of the solution of this partial differential equation. So finally, when I was 52 years old, I was like, no, I didn't. I figured this out when I was doing this. I was like, oh, that's why the orbitals are shaped that way, because that's the solution to this partial differential equation. It was pretty cool. So the first time I'd really understood the mathematical background of why that's the case. So anyway, it's nice when you have an opportunity to apply the divergence theorem. So let's look at an example. Which one do I want to do? We'll do that one. So we want to evaluate this surface integral, our flux integral, f dot n ds. The other way you might be asked this question is the outward flux of F through the surface and our surface our field F is xy I hat plus yz j hat plus minus yz k hat. And our surface is given by z equals square root of a squared minus x squared minus y squared. That's an a. And z equals 0. So what is that surface? A sphere? But what is this z equals 0 telling us? Top half of the sphere. So this is an upper hemisphere. This is an upper hemisphere. So it's a closed surface. We have a spherical surface on the top, and we have a circular bottom on this sphere. So we want to find the flux outward through that. Without the divergence theorem, we would have to we'd have to do two surface integrals, one for the spherical portion and one for the bottom. But since it's a closed surface, we can apply the divergence theorem. So we're going to say, I'm going to rewrite the divergence theorem here that lets us do this. Surface integral f dot n ds, our flux integral, equals a triple integral over d, and this is going to be nice. Our setup, the divergence of f through the volume. What kind of coordinates are you going to guess we're going to use here? Spherical coordinates. Nice, because we're talking about the top half of the sphere. Our limits of integration are going to be nice and easy. The divergence, del dot f. And remember, the divergence is a scalar, and it's just the partial of the x component with respect to x, partial of the y component with respect to y, partial of z component with respect to z. And we get y minus z, plus z minus y equals z. Partial with respect to x, partial with respect to y is z, partial with respect to z is negative y. All right, our solid region is bounded by, or given by this surface. We have this upper hemisphere. What is the radius? A. Radius is A. Bounded on the bottom by a circle in the xy plane. And we're going to integrate. We're going to turn this into a triple integral. In spherical coordinates, z equals rho cosine phi. And the thing that drove me crazy doing that PowerPoint is in the Windows equation editor, phi was not a symbol that you could just click on, so I had to insert a symbol every time. Yeah. What's that? I did, yeah. But then if I was doing a lot of those, that was good, but there were other things I needed to copy to the clipboard as well. All right. We have the integral. Theta goes from 0 to 2 pi. The integral phi goes from 0 to pi over 2 to get that upper hemisphere. The radius, rho, goes from 0 to a. Rho cosine phi times dv, rho squared, sine phi, d rho, d phi, d theta. Nice, easy integral to evaluate. Because we just have a rho cubed from 0 to a. So we get an a to the fourth. A to the fourth over 4. We end up with a sine squared over 2 for our phi integral from 0 to pi over 2. And then we just have a multiple of 2 pi from our theta. And we end up with pi a to the fourth over 4.
I don't.
And yeah, if a was so a to the fourth over 4 would have to be about 4. So yeah, for it to be 12.
Oh.
Yeah, so you just have to pick the right radius, and it would equal 12.
Yeah.
All right. Finally, now we can talk about a physical interpretation of the curl, or sorry, the divergence. Not yet. Interpretation of the divergence. Well, now with the divergence theorem tells us, again, that for a closed surface, f dot n ds is a triple integral over the solid region of the divergence of f dv. All right, so we're going to imagine a tiny surface. The flux through the surface is approximately, if it's very tiny, the divergence of F times delta V. It's approximately. And delta V is the volume enclosed by that tiny surface. So we're assuming that the surface is tiny enough that the field F is basically constant over that tiny surface. So this del dot F is a constant, and we're just multiplying by the volume here. Well, so what we're saying, we can write this as an equation, is that the flux is approximately equal to del dot F delta V. That's what we're saying here. Or the divergence of F is the flux over delta V. If we let delta V become very small, in the limit, and this is kind of argument by vigorous hand waving here. We're not being really technical. As delta V approaches, yeah, we're not doing mathematics. We're saying, well, if you think about it, this makes sense. As delta V approaches 0, we can say that the divergence of F equals the flux per unit volume at a point. The flux per unit volume at a point is the rate at which density is increasing. So the divergence at a point tells us, if we're thinking of our field as a liquid that has our field is a velocity field for a liquid, the divergence tells us the rate at which the density is increasing at a point, or decreasing, density is changing at a point. So that's when we said the divergence has something to do with the field flowing. It tells us that if we think of it as a liquid that's flowing around inside a solid or inside a region, the rate at which the density of that region is decreasing if it's flowing out, or increasing if it's flowing in. And we classify the divergence based on the sign of the divergence. So if del dot F is greater than 0, we call F a source. SOU. So the flux per unit volume is increasing. The stuff is flowing in. If del dot F is less than 0, we call F a sink. So when you have in your computer, when you have they call them heat sinks. That's the idea of a sink. Sorry, I pointed my inequality wrong way.
The alligator voice.
Del dot F is less than 0. F is a sink, so that means that something is flowing away. So a heat sink in your computer, something that's letting heat flow into it. It's sinking the heat. It's taking the heat into itself. And if del dot F equals 0, F is
CPU source.
incompressible.
Sean, well, you were not right.
So that means that the volume, the density is not neither increasing nor decreasing. So it's not changing at all. It's incompressible. All right, so now we have a physical interpretation, finally a physical interpretation of the divergence. We said it has something to do with something flowing. Well, now we can say the divergence is the flux per unit volume at a point. All right, questions? All right, last topic. So we're going to talk about this. I'm going to back up here really quickly. This tangential component of Green's theorem. We're going to extend that to 3 dimensions. That's what Stokes theorem does for us.
Is that what your shirt's about?
That is what my shirt's about.
It's Stokes Theorem.
wasn't the first one to come up with that. So it all comes back.
So this is 15.8, Stokes theorem. Stokes theorem tells us the line integral around a closed curve of f dot dr is equal to the surface integral of del cross f dot n ds. So really it's just an extension of that, what we talked about with Green's theorem, to 3 dimensions. Now our curve is a boundary of a solid surface. So S, not a solid surface, but a surface. S is an orientable surface. Bounded by C. And n is our unit normal vector. So what this is telling us is the tangential component of f integrated around the boundary of this curve is equal to the normal component of the curl integrated over the surface. So we're integrating the normal component of the curl. We use Stokes theorem mainly, one way mainly, but we can use it in 2 ways. One is to simplify a complicated line integral. This is the way we usually use it. So we turn a complicated line integral into a surface integral. And we'll take a look at an example of that. The less common way that you'll see it used is turning a complicated surface integral but it has to be, the reason this is used less is it has to be the surface integral of the curl into a line integral. So we have a complicated surface integral of the curl of a field, we can turn it into a line integral. All right, I just want to look at one example. This is our last example. One example of using Stokes theorem. Now this is, and that's a nice thing about Stokes theorem and the divergence theorem, is that it's supposed to make your life easier. I want to do this one. So we want to find this line integral. Now you won't always, the problem won't always say use Stokes theorem. You might need to decide for yourself that you need to use Stokes theorem. X, Y, Z I hat plus Y J hat plus Z K hat. X squared plus Y squared is less than or equal to A squared. Our surface, well, let me do it this way. C is the curve of intersection
Oh, wait, that would be more work.
of Z equals X squared, Y equals 0, Z equals 0, and X squared plus Y squared equals A squared in the first octant. So C is that curve of intersection. Well, let's try to draw a picture of this thing. So what is, let's start here. What is X squared plus Y, well, what is Z equals 0? XY plane. So that's the bottom of our, that's one of the surfaces that we're talking about. Y equals 0? XZ plane. So we're bounded by the XY plane, the XZ plane. Z equals X squared? What is that? Parabola. And Y can be anything. So we get a parabolic cylinder, but we're bounded by Y equals 0 and Z equals 0, so we get half of this. So our surface, part of our surface, is like this.
Whoa.
Half of that parabolic cylinder. What's X squared plus Y squared equals A squared?
Circle.
And Z can be anything. So that's a cylinder. So our other surface in the first octant is where we are. Let me try to draw this a little better. Is like this. We're talking about the curve of intersection. So our cylinder is going to come up here, and we're going to get a curve that goes down the surface like this. Should be probably a little more curved. So the curve of intersection of those three surfaces is, let me highlight it in a different color. There's my palette. I want red. Okay. The curve of intersection is going to be this thing. And in positive orientation, we'd be going that way, around the curve. So in order to do the line integral, we would have to parameterize that piece, which is where Z equals Y squared and X squared plus Y squared equals A squared. We'd have to parameterize that curve of intersection. We'd have to parameterize the curve along here, and we'd have to parameterize the curve here. That one's not bad, but we'd have three line integrals with three separate parameterizations.
But, hey, guess what?
But we can use Stokes theorem. If we use Stokes theorem, what is our surface?
That's a good question.
So the Stokes theorem says that the line integral, we can do the surface integral over the surface that is bounded by the curve.
Right.
So what
It's like a curve.
what is the surface that's bounded by that curve? Isn't it just Z equals Y squared?
It sure is.
That's the surface is bounded by the curve. Is Z equals Y squared. And our region in the XY plane is X squared plus Y squared equals A squared. All right, so we're going to apply Stokes Theorem. That's going to be our surface. We just need to find the upward component of the curl of F through that surface. So we're finding the flux of the upward component of the curl through that surface. So our flux integral is the flux integral of the curl. So we need del cross F. We need the curl of that field. So I'm just going to write it out here, just so we remember how to calculate the curl, because it's been a little bit. And we have x, y, z, y, and z. When we calculate that curl, we get x, y, j hat. Minus xz k hat. Not a difficult one to calculate. All right, so our surface. Do we have z equals f of x, y, z? Or it's g equals f of x, y, z? G equals z minus y squared. And that equals 0. So now we have, is it x squared? Did I miswrite it? Yes. Now we have g equals f of x, y, z. So we're going to evaluate del cross f dot del g. So with Stokes' theorem, we get to find the cross product and, or if we get to find the curl and the gradient. Del g is minus 2x I hat plus k hat. And we're going to do del cross f dot del g for our surface integral, for our flux integral, is minus xz. And on the surface, we're going to do the integral, double integral over a region in the xy plane. On the surface, z equals x squared. So this equals minus x to the third. All right, so what we're evaluating is a double integral over a region in the xy plane of minus x to the third dA. And this region in the xy plane is a circle. So what are we gonna, how are we gonna evaluate this? Polar coordinates. So we use polar, and we get the integral from 0 to pi over 2, integral from 0 to a, minus x to the third is minus r cubed cosine cubed theta, r dr d theta. Well, the r integral gives us a minus r to the fifth over 5, evaluated on 0 to a. So we get a minus a to the fifth over 5, integral from 0 to pi over 2 of cosine third theta d theta. And we know how to do this, right? What do we do? Substitute. So this is going to equal minus a to the fifth over 5, integral from 0 to pi over 2. I'm going to substitute for cosine squared, a 1 minus sine squared. So we get a cosine theta minus sine squared theta cosine theta d theta. And that's a nice, easy integral to evaluate. And I get, when I evaluate this, minus 2a to the fifth over 5.
Which obviously equals 12, yeah.
Right, if you pick A correctly, you could equal 12. All right, I think there's a little work there, but I think that's easier than evaluating those three line integrals.
Probably.
But those three line integrals are pretty simple, right?
This one's not too bad. That's not too bad. But you have to do three of them.
Yeah.
Now Stokes theorem, again, Stokes theorem is a generalization of the fundamental theorem of calculus because it says the integral of some quantity over a region is equal to some other related quantity on the boundary of the region. And in fact, Stokes theorem, you can derive the divergence theorem, Green's theorem, fundamental theorem of line integrals, and the fundamental theorem of calculus from Stokes theorem. Stokes theorem is kind of the most general statement of the fundamental theorem of calculus, because all of the others can come from Stokes theorem. So basically almost everything we've studied up until now, you could start here and get almost everything that we've talked about, which is kind of a cool thing. Pretty much. So, and now with Stokes theorem, we're at the end of the kind of the classical calculus sequence. Beyond this, there's applications of calculus, but there's not a lot of new stuff. You're applying what we already know.
So we've learned calculus.
You've learned calculus.
Yeah, but
We've been presented with
You've been presented calculus, yes. All right, interpretation of the curl.
Wait, I thought we were done. I thought we were done. Oh, come on. What is this?
Did you say we were done?
Well, we've learned everything, but we haven't interpreted everything.
Oh, okay.
We need to interpret the curl.
Technical.
We
the curl is the change in
yeah, we talked about curl being a tendency of a field to rotate or cause rotation. So Stokes theorem says the line integral f dot dr, the tangential component of our field, is equal to the surface integral of the curl of f dot n, so the flux of the normal component of the curl over the surface. All right, we call this line integral the circulation. Because what that line integral is, we're integrating the tangential component of the field around the curve. So that tells us something about the field circulating around that curve. We call that the circulation of F. So we can rewrite this equation as the circulation of F equals the curl of F dot n, I guess I don't need that, ds. All right, so imagine a tiny piece of surface. Like we did with the divergence theorem. And we're going to say that the curl is nearly constant. It's so small that we can say that the curl is constant at that point. And our unit normal vector then is nearly constant. So we can say that the circulation is approximately equal to the curl of F dot n times the double integral of ds over the surface area. So we're imagining this tiny piece of surface, so the curl and the unit normal vector are essentially constant. Well, what's the double integral over our surface of ds? This is the area. That's the area of the tiny surface. So we're going to divide both sides by that area, and we can say that the circulation over the area approximately equals the curl of F dot n. As the area approaches 0, so we take the limit as area approaches 0, see that the F dot n, the curl of F dot n, equals a circulation. Of F about n. So the normal component of the curl of F dot n, tells us the tendency of the field to cause a rotation about that point. So if you think of a normal uninormal vector at a point, the normal component of the curl tells you the tendency of the field to circulate, to rotate around that point. So if you're thinking of the field, F being a velocity field for a liquid, if you put a little paddle at a point, the normal component of the curl would tell you the tendency of that paddle to turn at that, around that point. So that gives us our physical interpretation of the curl. Normal component of the curl tells us the tendency of the field to circulate about that point around the normal vector. All right. Questions?
Oh, we're done?
Almost.
Oh.
The most important part.
Oh, word. Of course. I don't know where I was expecting.
We're done with.
Yeah. Oh, we're in math class. We have pi. Hey, do you want to know what else?
It is Star Wars Day tomorrow.
Oh, dude, let's all dress up.
Well, Connor, if you don't dress up, I'll be disappointed.
Alright, I'll just make sure you dress up.